What word is in optimization, or what words can come? Optimal, optimist, prime? That could be true. Anyway, so. Maybe optimist and prime. Anyway. I was thinking prime isn't like a derivative. So then coming back. For optimization, what's the long story short? Snazzy word, but we don't even have to remember it, I promise. You don't have to remember optimization. But what you do have to remember is if you read a problem and you figure out that you're supposed to find a min or max, you need to know how to go about doing it. So in order to figure out whether or not you're supposed to do a min or max, hopefully you read the problem, you figure out what's the givens, what are the givens, what you need to find, and draw a picture. This sounds a lot like related rates. That's a good thing. Because you come to a word problem, and you read it, you figure out your givens and your find, and draw a picture if possible, and label it, right? So all word problems kind of start the same. Who's the primary equation? Where does he come from? He comes from whatever you're supposed to be maximizing or minimizing. He's the key to the problem. He's the, I shouldn't say the key, he's the point of the problem. He's the objective. He's the guy that needs to be maximized or minimized. Secondary equation, sometimes he's there, sometimes he's not. Secondary equation, sometimes there's an extra restriction, an extra, what am I trying to say? There's a good word for it, and it's not coming. It might come a little bit later. But sometimes there's some sort of extra piece of information that needs to be true. Some sort of extra, it's not a limit, but no, it's not there. That needs to be true as well. And so in a sense, we need to incorporate this into that. If there's some extra piece of information, we'll go back to the fence one and see where or why that one does have a secondary. But long story short, this equation, before you maximize or minimize, before we do calculus, before we take a derivative, we need to get this equation in terms of one variable. What does that mean? You're allowed to have a variable on this side. Y equals, A equals, Z equals. You're allowed to have a variable here, but on the other side, it needs to be in terms of only one. It's not like related rates, how we can take an equation with lots of variables and take DDT and say like, oh, dRdt, dAdt, dVdt. It's not like that. We have to keep it in terms of one. Then we check to say, are there endpoints, and then we do our calculus. What calculus? Critical numbers. If there are endpoints, we do a table test to do absolute extrema. If there aren't endpoints, probably a quick little sign chart will be enough to say, yep, that's going to be the definite, the absolute min or max, and we're done. Question, why was this a max-min problem? Remind me. Where in the wording? As small as possible, and what else?
As large as possible.
All right, so in the wording, it didn't necessarily say max-min. It's not like those ones in the chapter test you just got back where it said find the relative extrema or find the relative min or the relative max. But it's in the wording. Question, did this one have endpoints?
Yes.
Yes, you can tell because I have a table. But then coming back, it was a closed interval. So we did have endpoints. We needed to go to a table. But before we went to the table, we don't just need endpoints. Who else do we need? Critical numbers. So for critical numbers, I need to do a pitchfork, but I can't do a pitchfork until I take a derivative, and I can't take a derivative until I get an equation. So we had to read, and we had to go ahead and see sum of number and reciprocal. Sum is of a number, we named it x, and plus its reciprocal, 1 over x. We had to pull that out of the wording. Then we were able to say, let's go, take a derivative, pitchfork, get our critical numbers, only keep the ones that fit inside the domain or the interval. So the only one that fit was 1. And then we went ahead and tested plugging into who? The original, right? And we just said, hey, whose sum is lowest and whose sum is highest? Were our answers the sums or the number? The number. Why? What did they say? Find the number. They didn't care about the sum. They just wanted you to figure out where or for what numbers the sum was lowest or highest. Okay. This is the one that we ended on yesterday. We have a guy who's putting up fencing. And heavy-duty fencing is more expensive than the standard fencing. He's trying to fence in a rectangular plot of land. We figured out $3 a foot for this one. We drew a picture and labeled stuff. $2 a foot for that one. The total cost has to be $6,000. Why is this circled? Max area. That's what we're trying to figure out. So who's going to be maximized? Who am I taking the derivative of? Area. So I start building my formula. Area equals base times height. But I just said a little bit ago, before we can take a derivative, we need area in terms of it is in terms of base times height, but what do I want it in terms of? How many variables? Just one. Well, stink. We have to somehow get rid of one of those variables. Another way of thinking about it is, let me get rid of that silly highlighter. Another way of thinking about it is there is a secondary condition that needs to be met. I don't have infinitely much money to build this fencing, to fence in this plot of land. I'm restricted, that's what I was looking for, restriction. Anyway, I'm restricted by, I only have $6,000 to do this, or he only has $6,000 to do this. So I can't just go using area without using this restriction or this condition. Now how can I use this condition? First of all, where did the 3 come from? Why is it 2H? Because there are 2 H's. And then 2 comes from? And then 2B, because how many B sides? So now I can go ahead and say 6,000. This is my secondary equation. This is my secondary or my extra condition or restriction that needs to be met. I'm going to have 6H plus 4B. Well, question, kiddos, how can I use this equation and get it into the other one to be able to go ahead and take a derivative? Solve for one variable and plug in, just a plain old substitution-y thing. Now, technically, it's up to you guys as to what we solve for.
I want B.
You want B? All right. B is better. Okay, so B is going to equal, can I do this fast? 6,000 minus 6H all over 4. Technically, we can, it's not going to go in evenly, but we could divide both by 4. We'd end up with, what, 1,500? Is that right? Minus 3 halves H.
Yes.
Just to make it a little bit prettier. And what am I going to do with this clue? What am I going to do with this information? And once I plug it in, I have an equation with one variable. I can take a derivative and I'm golden. So, yeah. H. Yeah. So H would be like our X. So he's going to be the one we're solving for critical numbers. So I get A is equal to, actually, are you guys okay? If I plug this in, the H, I'm going to distribute it in. Is that okay? Just to make it easier. So the H is going to be times 1,500.
Would that be easier to do that?
Yeah, right? Because now I can do power rule instead of product rule.
Are you supposed to put an H in it or something?
Oh, I didn't even put it today. I was skipping ahead to the derivative in my head and then I went back. Okay, does that make more sense? The H distributes to, there's our B. So there's an H times 1,500 minus an H times 3 half H. Okay, so we have our function in terms of one variable. Now I'm going to take a derivative because I'm trying to find my critical numbers. Derivative of 1,500H is just 1,500.
Yeah.
Bring down the 2, I have 3H. Set equal to 0. My critical number is at 500. Oh, wait a minute. Do I have to do a table test? Oh, stink. Hold on. We have to do a table test of the critical number with the endpoints. Oh, they didn't tell us domain. Maybe this is one we're supposed to figure out ourselves. That was one of the steps to consider domain. Who's my variable? H. How small can H be?
No.
But would that really make a rectangular plot of land if H was 0?
No, it's a 1.
So, even though you're right, don't say 1, because H could be 1/2, and I still have a rectangle. But couldn't I say H is within and make 0 open? Just be like, well, it can't be 0, but it can be, I guess, anything greater than 0? But it's not closed, so it's not an endpoint. Oh, okay. How big can H be? Infinity! No, 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 you only have $6,000.
2,000.
If you think about H, if you only had one line of H, well, I guess you have to have 2 lines of H, right? But I guess B could be 0.
This is 2.
We could say 2H times 3, which would be 6. No, H can't be very big. He can only be 1,000. Right? Because if he was 1,000, he would be 1,000. I'd have 2,000 times $3. I would spend all my money on my heavy-duty fencing. So H could only be 1,000. But either way, kiddos, are either of these endpoints? If H was 1,000, I'd have no money for B, so B would be 0. That wouldn't be practical. It wouldn't be a rectangle anymore. So do you see how they're not even endpoints?
Yes.
They're not even endpoints. Guess what?
Don't care.
Here's our answer. Dun, dun, dun. Now, if you're like, I don't trust you, what? It's a random number that we got. Technically, how would we show it? We would go ahead and do a quick little sign chart and say, okay, if we go from 0 to 1,000, 500's in the middle. Guess what would happen if we were to plug into A prime? 1. It'd be a positive. How about 600? It'd be a negative. And guess what's at 500? A max. And if it only increases and only decreases, that has to be the highest. So that could be our little justification, our rationale. But the nice thing is, 500, that's our height. Are we done? Is that what they wanted? Ooh, what did they want? Dimensions. So we have half the dimension, right? Whenever you talk about dimensions, you want the length and the width, like a 4x4 or something like that. If you're going to like a store to try to pick up a piece of wood. So in this one, 500 is good, but what else do I need? Good question. Don't I have an equation? But if I have H, I can find B. You can plug in here or here or here. All of them are good. But long story short, if I was to plug in 500 to find B, I'd have 1,500 minus 3/2 times 500. Real quick. 500 divided by 2 is 250. 250 times 3 is going to end up being 750. So then B equals 750. 1,500 minus 750 is another 750. There are my 2 measurements. So my final answer, if I was to state it in a nice answer, like a nice sentence form, my area will be maximized when the dimensions of the rectangular plot are 500, what am I labeling stuff in?
It's a feet.
A foot, good. 500 feet by 750 feet. Am I multiplying? No, it's just a silly way of writing dimensions, right? Write the word by. 500 by 750. Dun 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 dun. Okay, so we did one that was kind of more mathy. We did one that was more practical application-y, if that's actually a word, which it's not. Let's go back to another one that's, What on earth? Did I open the wrong period's notes? No, that's you guys. Huh. Alright, kiddos, for some reason, the changes I did this morning did not save. Let me go find someone else's. Because you don't want to do that example. I have better examples for your homework. Give me 1 second. That's not you guys. That is you guys. That is the weirdest thing. So how are you? Good. Question. You know how we had that mathy one that said find a number and we called him X? What if there was a problem that said find 2 numbers? X and Y? Ooh. What does sum mean in math? S-U-M? Plus. What does product mean in math? Multiplication. So, when I show you this example, haha, there you go. I want you guys to try to write in a mathy statement, aka an equation, what they're talking about. Ready, set, go. Try to analyze and translate the wording into mathematical statements. Don't worry about necessarily what to call everything, but I would say two positive numbers. I would say let's make them x and y. I would say let's make them x and y. Alright. If we were to work this out. Yeah.
Is 0 a positive number?
Usually 0 gets lumped in with positive. Technically it's neither. Positive nor negative, but you can get lumped in with positive, I suppose. Let's see, what are we given? Find. Two positive numbers. Oh, alright, fine. X and Y, right? Aren't we given the sum of the first number and twice the second number is 108? Isn't that like a statement? Like that's a condition or a restriction? How would you write that in a mathematical statement? The sum of the first number. Good. Good. And actually, technically, this is kind of our restriction. Remember the cost, how that restricted us? This is going to restrict us too. That's our secondary equation. That's our clue that we might have to come back to. But hold on, what's our objective? What are we trying to do?
I made it Z.
We're trying to find two positive numbers, but we're trying to make the product a maximum.
That's what you.
So we're trying to maximize the product. That's what we're trying to do. But we're trying to find the two positive numbers that will maximize the product. Let's see, what's my equation then? Product of who? Oh, x times y. But wait, that's not an equation. Where's the equal sign? You make them an equals. He's not a number. We don't know the number. The whole point is that we're supposed to figure out what maximizes him. So we can just say product equals. We can just make that our primary equation. If you ever are like, wait a minute, I need to make up a letter, just make up a letter based on maybe the word that it's called, right? Like we did with sum. We just called it S. Product, we can call it P. But wait a minute, if this is our primary equation, we need to take his derivative, but is he good the way he is? Or does he have too many variables? Oh, that's okay, because I need to bring this restriction in, right? Well, how am I going to bring that restriction in? Plug it in, substitute. We could solve for x, we could solve for y. What would you guys rather solve for?
I like Y.
Yeah, I like y too, right? So we can do 108 minus x over 2. Oh, maybe I like x better.
Yeah.
Because otherwise you're going to have to divide by 2. Now some of you are like, but I don't want y's, I want x's. You do you. It should work out either way. We like this one because then we don't have to divide by anybody funny. We can take them, we can plug and chug them, and we can write our nice primary equation in terms of one variable. What do you guys think? Derive or rewrite? Oh yeah, rewrite. Let's distribute, right? 108y. This is what I kind of did quickly in the problem before. You guys caught me though, I did it wrong the first time. What's our goal? What are we supposed to be doing?
Finding the max.
Finding the max, but to do that we need to find our critical number. So P prime, 108,
Minus 4y.
set that equal to 0, and that's going to happen when y is equal to, what's 108 divided by 4? 27. Oh, stink, endpoints. Brandon was talking about that a second ago. He was like, oh, two positive numbers, what's the lowest y can go? Oh, is there a top one?
Yes, there is.
Ooh, it's bound by 108. So if x was 0, question, what would y be? 54. Oh, wait. What if y was 0? What would your product be? If y was 54 and x was 0, what would your product be?
So that means that
So maybe 0 shouldn't really be included because he isn't really practical to the problem.
Smart.
So we can make it open. That's a way of thinking about open and closed bracket. Yeah. Oh, remember we're stuck by this. So if x was as low as he could go, which is 0, he can't go negative. What would y have to be? Divide 108 by 254. Yeah. But either way, guys, endpoints? No. Oh, cool. Well, if there aren't any endpoints, guess what? Guess who our answer is? Could I prove it with a sign chart? I could prove it with a sign chart, but we're good. We don't have to do a table test. We had no endpoints anyway. So then we can go ahead and say, what are we supposed to find? 2 positive numbers. So if y is 27, 2 times 27 is 54, subtracted from x is 54. So I can say one number is, the other number is, dun 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 dun. Dun dun. Okay, we did one that was kind of more mathy again. It wasn't like someone building something or buying something. Katrina.
No, I was gonna say, is it 54, that was just for one. You have to find the lead for x as well, or is it?
Technically, no, because if we restrict y, then we're going to find, like, if there are 2 different answers, when we find one, it's going to be a legal answer for the other. Because if we keep that one legal, he's going to have the other one legal. Okay. Let's go to another mathy one, but a bit different. A bit different. We're not talking about sums or products, but we're also not talking about areas and perimeters. Ooh. Why is this? Why is this a max min problem? Yeah, do you guys see the S? Do you see the superlatives? Closest to? And the greatest? Closest and greatest? What are we talking about? We're trying to find the min and max. These are the one they want to know both. The min and max who? Closest and farthest. What dimension, what quantity are we talking about? Distance, yeah. We're trying to find the greatest and the least distance. Here's our wording. What are we given? Well, y equals square root of x. Well, that's a restriction, right? Let's see. We know our domain, x has to be in between. Closed interval, which means do we have endpoints? Ooh. Anything else? Distance to and from the point 2, 0.
The distinct formula.
Yeah. We need to make a formula. We need to get an equation, and we need to do it for distance. Okay, cool. How do we find a distance formula?
Square root x squared plus y squared plus d.
Change in x squared plus change in y squared is d squared, yeah. Or we could say d is equal to the square root of, this is one you're more used to, x minus x, or like x2 minus x1 squared plus y2 minus y1 squared. But wait a minute, do we know an x1 and an x and a y1?
Maybe.
Don't we? We know a point. So let's go ahead and just do x minus 2 squared plus y minus 0 squared. And that's kind of like my x2, x1, y2, y1. We only have one point, so we'll plug in that x and that y, and we're left with another x and another y. I just think we have too many variables again.
Maybe.
Wait. Don't we have a clue
Yes.
that relates the two? That we can write in blue? I don't know. To plug into the other equation?
Square root of x equals 1.
You don't even have to do anything. Look, can't you just go in? So let's get rid of that y. It's in our way, and we have something that can substitute for y. So we're going to end up with d is equal to the square root of, well, let's FOIL him out. Because if we have to take a derivative, we don't want to leave it looking like that, do we? Don't. CalcAB, FOIL correctly, x squared minus 4x plus 4 plus, plug in, y is square root of x and square that puppy. Y minus 0 is just y, plug in square root of x. Oh, what does this become? Yeah, negative 4 plus 1x. So I have x squared minus 3x plus 4. Thank you, man. Aw, don't we have to take a derivative?
Yeah.
Okay, wait. There's something really cool about minimizing and maximizing distance. Because if you look at him, you're like, oh, this is disgusting. Except, when is distance going to be the smallest? When the inside part of the square root is going to be the smallest. So if distance is going to be the smallest, when the inside part is the smallest, because everything's going to have a square root, well, can't I just say, hey, I just want to worry about the inside part?
We can do that.
Yeah, that's the cool thing about distance. Because if I want to minimize or maximize distance, I just need to minimize or maximize what's under the square root. Now, they're not asking me specifically. I'm not answering with the derivative. If I was, this is totally illegal. I have to take the derivative of the whole thing. But since I'm just trying to minimize or maximize, well, when's the highest D going to happen? Well, when the inside's the highest. When's the lowest D going to happen? When the inside's the lowest. So I can cheat just a little bit. And the example in the book that's kind of similar to this one does the same thing. We can just look at the inside and say, hey, when are you the highest? When are you the lowest? How do we figure that out? Derivative. Isn't that a lot easier for your derivative?
Yeah.
Oh, yeah. We solve. X is equal to 3/2. That's the answer. Wait, they asked us two things. And we have endpoints. What are we supposed to make? Nice. I see some of you already making it. We need to make a table. For absolute extrema. We need our X. We could do little d or big D. Either one. We're looking for the highest and the lowest. We just have to make sure we plug into the same equation. No derivative though. We're plugging in our endpoints of 0 and 3. Oh, we'd better ask ourselves the question, does 3/2 go in between?
Yeah.
Good. If it didn't, we would just ignore him, I guess. If we plug in 0, we end up with 4. If we plug in 3, we end up with 4. If we plug in 3/2, we end up with
Some negative number.
3/4 minus 9/2. Ugh. No, 9/4. That's what 9/4 minus 9/2 plus 8/2. That'd be 9/4 minus 18/4, which is negative 9/4 plus 16/4. 7/4. Is that right?
That's what I got.
Sweet. So question. For the min distance or closest to, and for the max distance, farthest from. Min distance. What's the smallest one? X equals 3/2, right? What's the biggest one?
0,3.
And they're actually, wait, did that answer the question? Find all
That
points. Oh, struggle. Hold on. They don't just want X. What do they want? X and? Okay. So we need to plug in. There's our 3/2. And square root of 3/2. Oh, this is nice. Why am I doing that? Y equals square root of X. Then I have my 0, 0, and I have my 3 square root of 3. Optimization. All it means is you gotta take a problem, figure out the math, and then use derivatives or table tests, well, derivatives and table tests, if there are endpoints to find the highest and the lowest. Cool kids, work on that homework tonight. I have particularly made it shorter so that you can really focus on each problem. And one more note, I've given you mostly odds, so you can not cheat, check. Get out your items. Not cheat, check. Bye, guys. Might do another example at the beginning of class tomorrow, but then homework questions. So let's see how we do.